Kimi K3 is a 2.8 trillion parameter Chinese model built while Washington tightened the chip pipeline. Yet the most important number is missing. Moonshot has not said what hardware trained it. No card count, no chip name, no cluster map. That missing number tells us how to read the whole story. This is not a story about a secret chip smuggling trick. It is about a harsher, more interesting playbook. Make the model activate less of itself. Make the cluster wait less. Make every memory byte work harder. Then ship the result through more doors than one closed API. The controls have not made compute disappear. They have made it scarcer, more uncertain, and more valuable. Think of them as a silicon tax. China can still build capable systems, but the cost curve pushes labs toward unusually aggressive software and systems engineering. First, what does the blockade actually squeeze? The target is bigger than a famous GPU. In December 2024, the U.S. Bureau of Industry and Security added controls on high-bandwidth memory. BIS calls HBM critical to AI training and inference at scale. It also tightened controls on advanced manufacturing equipment and software. That is pressure on compute, memory, and the future supply chain together. But it is not a simple on-off switch. In January 2026, BIS said H200, AMD MI325X, and similar applications would be reviewed case by case under conditions. That does not mean easy access. It means supply has channels, rules, delays, and uncertainty. A lab plans around all four. Here is the discipline the K3 story demands. AP reported that Moonshot had not said what hardware built K3, so claims that K3 ran on a particular mix of H100s, H200s, H800s, Ascend chips, or overseas cloud are not a reconstruction. They are guesses. The engineering mechanism is visible. The exact cluster is not. The first escape hatch is mathematical. A dense model wakes nearly every parameter for every token. A mixture of experts model keeps a crowd of specialists available, then wakes only the few it needs. Moonshot says K3 has 896 experts and activates 16. That is the core trick. Make the model enormous in total capacity without charging every token for the whole building. Do not turn that ratio into magic. All those weights still need storage. Experts must be rooted, balanced, and connected. Training still costs a fortune. Sparse models do not repeal physics. They change where the bill lands, less arithmetic per token, more pressure on routing, memory, and communication. Moonshot names stable latent MOE, Kimi delta attention residuals, quantile balancing, and gated MLA. It says this design improves scaling efficiency about 2.5 times versus K2. That is a company claim, not an independent audit. But it tells us what the lab is trying to buy, more capability from each unit of compute. Now look at the public precedent that makes this believable. DeepSeek v3 published the numbers K3 has not. Its report describes 671 billion total parameters, 37 billion activated per token, and 14.8 trillion training tokens. It reports 2.788 million H800 GPU hours for full training. The report also says that total excludes prior research and ablation work. Read the number as a disclosed run, not the price of discovering the recipe. A deeper lesson is co-design. DeepSeek describes multi-head latent attention, FP8 training, load balancing, multi-token prediction, and dual-pipe pipeline parallelism. In plain English, shrink the memory burden, use lower precision carefully, keep experts evenly busy, and do useful calculation while data is moving through the network. The cluster spends less time waiting. That is evidence of an engineering path, not a universal blueprint. DeepSeek disclosed, and a detailed technical report. Moonshot has not disclosed K3's cluster. One model can prove that constrained hardware plus disciplined systems work can reach far. It cannot prove every later launch used the same route. Training is only half the contest. The other half is how capability spreads. Moonshot says K3 is available through Kimi's app, website, work product, coding tool, and API. That matters because deployment is an economics problem too. A lab can steer easy requests to cheaper paths, reserve expensive thinking for hard jobs, cache repeated context, quantize where it is safe, and spread traffic across infrastructure it controls. The open weight claim needs a date stamp. Moonshot says full K3 weights will be released by July 27th. Today is July 19th. Scheduled is not shipped. If the weights arrive, outside teams can host, adapt, and quantize the model themselves. But weights are not the same as releasing the training data, the whole recipe, or the bill for the cluster. Why does that delivery route matter? The The UK AI Security Institute says the broader gap between open and closed systems is now 4 to 8 months, depending on the evaluation. That is not a K3 score. It is a broader trend. A shorter wait gives companies more leverage, more fallback options, and less reason to build their entire future around one rented model. So did efficiency beat the blockade? Not quite. Moonshot itself recommends deploying K3 on supernodes with 64 or more accelerators. That one line ends the fantasy that clever code has made hardware optional. At frontier scale, the bottleneck keeps moving. Compute, HBM, network bandwidth, power, cooling, and software stability. Engineering can bend each constraint. It cannot erase all of them at once. That is why the honest conclusion is neither China has been stopped, nor China has made the controls irrelevant. The policy raises cost, adds uncertainty, and constrains the ceiling. The response improves the software below that ceiling. The contest is now about whether better algorithms and systems improve faster than the hardware gap widens. Kimi K3's real lesson is not that a silicon blockade failed. It is that a blockade changes incentives. Scarcer hardware rewards sparse models, low-precision training, better routing, smarter scheduling, and flexible deployment. K3's hidden cluster keeps us from telling a fairy tale. Its visible design shows the actual strategy: convert every expensive watt of compute into more useful intelligence.